Hello, and welcome to this edition of the CSIAC podcast series. This is a multi-part series on the new Rust programming language, which was developed with the goal of being a safe systems programming language. In this series, entitled Rust Models, CSIAC subject matter expert, Dr. James Fawcett, will examine, explore, and describe different conceptual models that underlie the Rust programming language. In the fourth episode of this series, Dr. Fawcett will discuss the Rust generic types, a language facility for defining types that depend on a parameter specified at compile time. Rust generics are similar to generic types used in Java and C#, but unlike C++ templates, which support specialization.
Good afternoon. My name is Jim Fawcett. This is the fourth in a short sequence of videos about the Rust programming language. In this video, we're going to focus on Rust generics. So generics provide a way of defining types that depend on a parameter that's specified at compile time. So we might create a library of generic types, and then when we enter main, we might specify, if we have a dependency on that library, we might specify, create an instance of that type with some specific parameter type. Okay, so Rust generics are very like C# and Java generics. They're simpler than C++ templates. C++ templates have a functional language behind them that supports things like specialization. So we define a generic a generic pattern for some set of types we want to create, and specialization allows us to refine that pattern for particular types. So a template or a generic, you can think of that as a code generator. The code doesn't really get generated until we supply some concrete type for that template parameter or for that generic parameter. Rust generics are quite like C# and Java generics, not like C++ generics. They have no specialization, but we can constrain them with something called traits. Okay, so in this block, we see some code that's very like code we looked at in the earlier demos, but here, now you see us providing a generic argument, a type T argument. T hasn't been defined yet. So in C++, we'd see a template type name T. That boilerplate we don't need to use that boilerplate in Rust. Very similar to the way C# and Java treat generics. And so here we have a demo and demo function, and it accepts this T by reference. And this is a constraint, where T:\debug. So this says that T must implement the debug trait, or this will fail to compile. As long as it implements the debug trait, then it should compile, as long as we don't do anything uncompilable in the body of the function. Okay. So this where clause is one way to constrain it. Another way to constrain it, this is another function, show type, T:\debug. So here, this is totally equivalent to this where T:\debug. It's just a shorthand way of saying that. If we have lots of constraints, we might choose to use the where clause because it gives us a little more room to string all that out, but either way is fine. So, let name equal standard, any type name colon T, and then size of T. All of that works as soon as I pass in a concrete type. So here, what I'm doing is defining a pair of functions, both of which will accept a large variety of types. It'll accept any type that implements the debug trait. And debug, if you remember, debug trait is just all that's necessary to allow the compiler to generate formatting for us in what it calls a debug style. Very simple, unadorned way of putting things out onto the console. And we can also have types that are generic. So here's a struct point T. So all its arguments are of type T. So this, could be a point in space. So this is height, width, and depth. Or, if there were 4 arguments, it might be in space-time, height, width, depth, and time, whatever. But anyway, so we can have generic functions. We can have generic types. Okay, so traits play a significant role with generics. And in a sense, they're something like what the concept will be in C++, or at least what I understand of concepts will be in C++. Perhaps a little simpler, because the engine, the underlying code generation engine is simpler. But anyway, traits provide this contract, function specifications that guarantee behavior. Any type that implements clone can be called by clone. We've seen this slide, if this looks familiar. I moved it, I copied it from the earlier presentation just to refresh your memory about what a trait is. So functions can accept either types or traits. And, the trait methods just become methods of the type. Okay, so now let's talk about implementing traits for generics. So here I have a generic type, struct point T, X, Y, and Z, copy and clone. And this will be, I can do this copy trait as long as T is a copyable type. If it's not, this will fail to compile. I could, if I want to support non-copyable types, I should remove this copy marker trait. Okay, and so as we saw in the last video, we can define traits. Here's a show trait that has a super debug trait because it needs the debug to satisfy the requirement to print using this debug trait. And I have a size trait that just declares a method, doesn't implement it. And I have a function that accepts a trait dynamically. It'll use dynamic binding via the traits virtual function pointer tables to do a dynamic binding. And this sizes function will accept both ordinary and generic arguments. Now, the purpose of this page is to show you what we have to do differently for when we implement traits and methods for a type. What do we do differently if that type is generic? So the answer is up here for the traits, and this function accepts the trait, nothing. It's exactly like it was for the non-generic example we looked at in the last video. But with this, when we go to implement the traits, now things are different. Implement T, show for point T. Now I have to say implement of T, and I have to say point T because this is the type. I didn't define a type point, I defined a point type of T. So I need this parameter T for the implementation. of the trait show for the point T type. And here, I'm just going to use, just like we did in the last video, I'm going to use the default implementation for show that I provided over here. Here's the implementation for size. And again, impl of T for point of T. And now size, use size is standard mem size of point of T. So I need to use the parameter to specify this point. I need to use this parameter to specify this point. Where does that come from? It comes from this parameterization of the impl. Now I can say type mute point equals, some values. I can say t.show, okay, because show is a method, and I can say print size of T, sizes of T, okay? So the only real difference here is implementing this generic type was very like implementing the non-generic type in the previous video. We just have this little bit of type decoration here. And that's enough to implement that code generation facility. The code generation is not exactly the same, but close to simply pasting the concrete type in for this placeholder T, okay? In C++, it's a whole lot more than that. In C# and Java and in Rust, it's pretty close to a placeholder pasting mechanism. So in summary, generics help us build flexible code. You saw us generate this function that accepted this type, so I can build a flexibility into my code using dynamic dispatching, but I can also build flexibility in my code by allowing the library to defer specification of this T, so I can build a container that'll take a whole variety of types. Instead of having to implement a container for each type, now I can, if I want a list container, I can do it for a whole set of types. So it allows me to be quite flexible. I can do the same thing. Suppose I wanted to build a directory navigator. And I got this nice little function that recurses its way down through a directory. And the only problem with it, should be reusable component, but the only problem is that I have to specify what I want to do when I encounter a file name or a directory name. What do I want this component to do with it? So now, under that scenario, I have to cut and paste the code to make it do application-specific stuff. But if I provide an application type that provides a do-dir and do-file method, now my navigator can just take as a template, as a generic parameter, take that application type, and the application type will determine what I'm going to do. So I have this nicely reusable navigation component, and into it I plug in whatever the application needs in terms of this little tiny application type that just defines those two methods. Okay, so gives us this ability to be really flexible, nice designs. You'll see quite a few examples from my GitHub website, which if you go to the very first slide on the first presentation, you'll see a link to my GitHub website. If you go there, you'll find examples of generic code where we're taking full advantage of that flexibility. So with that, I'm going to stop here. Next time, we're going to talk about code structure in the next video. This one, a fairly short video, because the next one we'll make up for it by being a little long in the next one. So with that, I'll just say goodbye. Goodbye, folks.
On behalf of the CSIAC, we would like to thank you for viewing this podcast. We hope you found the content useful and informative. If you would like to provide us with feedback, please comment on this video or visit our website at www.csiac.org, where you can also find additional content to review. Thank you.
Did you know that CSIAC offers free monthly webinars featuring experts in the areas of cybersecurity, software engineering, modeling and simulation, and knowledge management? Come see leading industry professionals talk about industry practices and leading research. Make sure to visit www.csiac.org/webinars in order to subscribe to our mailing list and see when the next webinar series is available. There you can also watch previous webinar series to catch up. Visit www.csiac.org/webinars.